Hi guys, welcome back. In this video, we're going to look at applications of the dot product. In particular, we're going to look at something called the projection of one vector, u, onto another vector, v. To recall, we've got two definitions of the dot product. You've got the algebraic definition of the dot product, which just says if you're taking the dot product of u and v, multiply component by component, and then add, multiply, and then add, and multiply, and add, and then you stop when you run out of components. So this would be our dot product in R3. That's our dot product in R2. The geometric definition, which allows us to give this dot product some meaning, is that the dot product is the length of u times the length of v times the cosine of the angle between them. So if this is my vector u and this is my vector v, and that's my angle theta, they have to start at the same place. They have to have the same initial point. Some people will say you have to draw them tail to tail. Theta is the angle between u and v when drawn this way. Now theta is the smaller of those two angles. It's not this one, it's that one. And even if v were down here, it's going to be the smaller one. So with that in mind, let's talk about projection. Now, before we give formulas for projection, I just want you to see that you've done this before. Whenever we look at v in component form, so let's say this is our vector v, and it has components v1, or v1 times I hat as its x component, its vector component, and v1 times j hat, or v2 times j hat as its y component. We've taken this vector v, which points in this direction. It doesn't point in this direction or this direction at all. And we've said it's convenient to write this vector v with one part of it pointing in the x direction and another part of it pointing in the y direction. It's convenient in a lot of problems in physics. Often decomposing forces into their components allows us to find the resultant force pretty easily. But we said that v1 times I hat and v2 times j hat are the vector components of v, in the x direction and y direction, respectively. And if we want scalar components, we're just talking about the length of each of those. So v1 and v2, those are just numbers. Those are the scalar components of v. In the x and y directions, respectively. Now, another name for this is the projection. I can think of this as taking the vector v and then projecting it onto the x-axis. So I could call these vector components of v in the x and y direction vector projections of v. Onto the x and y axis. So that's the vector projection in the x direction. That's the vector projection in the y. It's almost as if you've got like a sun up here, and you're saying, okay, well, what's the shadow going down from the sun onto the x-axis if the sun is above v up here? Well, then we're going to see this. Or if the sun was over here, the shadow that v would cast on the y-axis, that's this vector. And we could move that vector over here so that we complete our triangle. So this is a vector projection, or you could think of the scalar projection, that's just the v1 and v2. So we've done projections before, we just didn't call it that. We called these projections components in the x and y direction. So projection is just another name for component. So we could call these scalar projections. So those are the same thing. And when we talk about taking U and finding the projection of U onto V, what we're implying is we want to split U into two parts. Just like we did here with V. I had one part of V in the x direction, and then another part of V in a perpendicular direction, which is the y direction. When I add those together, I get V back. Here, what I'm doing is I'm splitting U into two parts. One part of U is parallel to V. So we're going to call that the projection of U onto V. And this is the part, or the vector part of U that's parallel to V. And we could call it the vector component of U, parallel to V. So maybe this is our vector V. It's kind of long. And here's our vector U. The projection of U onto V is the shadow that would be cast if I had a sun right here and splitting U into two parts. One part that's parallel to V and another part that's perpendicular to V. And use a straight edge to draw that in. Oops, here we go. Part that's perpendicular to V. It's right here. This part we're going to call W, and this part down here, the component of U that's parallel to V, that's the projection of U onto V. And again, if you want to think of it intuitively, you can think of it as like a shadow being cast. Here, if the sun is directly above V, the shadow that V casts on the x-axis looks like this. If the sun is over here on this side, the shadow that V casts on the y-axis looks like that. It's like our sun is on a line that's parallel to V, and it's just like right up here. I say, okay, what shadow does U cast on the line determined by V? That's the projection of U onto V. So that's that vector. And then the other part of U, we're calling that W. We're going to call that the vector component of U. Orthogonal to V. And remember, orthogonal just means they meet at right angles. I'm thinking of this vector and this vector as perpendicular. But when we're talking about vectors, we tend to use the word orthogonal. We could also use the word normal. But again, we use those words in different contexts. When we're talking about comparing vectors to vectors, we say that they're orthogonal to each other. So this guy is orthogonal to this guy. And this is the part of U that I have to add to the projection to get U back. So I've got part of U in the V direction, part of U that's perpendicular to V, and then when I add them, I get U. Just like over here, I've got part of V that is parallel to the x-axis, part of V that's perpendicular to that, and when I add these together, tip to tail, I get V back. The same is happening over here. Now by design, since this is the part of U that's parallel to V, and this is the part of U that's perpendicular to V, if I add this guy to this guy, I should get that guy. So just by design, it's a fact that the projection of U onto V plus W is going to equal U. So this is the component of U, vector component of U, parallel to V. And this is the component of U that's perpendicular to V or orthogonal to V. I'm just going to use that sign for perpendicular. Okay. Now, you might say, I'm really not sure when I would ever use this idea, but the truth is you have done it before. If you've ever taken Physics 1, you've probably seen this problem a million times. Just remember the box on a ramp from physics. You've got some box on a ramp, and maybe you know the angle of inclination of that ramp. Maybe it's like 35 degrees or something like that. And the weight of that box is pulling it straight down. And the weight is mass times gravity. But you say to yourself, yeah, that's really easy to describe in rectangular coordinates in this coordinate system. It's really easy to see that that's just negative mg in the y direction only. But that doesn't help me. I want to know what part of that force is pulling my box down the ramp and what part of that force is keeping the box on the ramp. This box on the ramp problem, this is just one variation on a theme. You may have seen a baby on a slide, a box on a ramp, a truck on a hill. I heard one recently about cyclists cycling down a hill. Basically, I've got this force that's pulling down, but I don't want to think of it as a force pulling down. I want to think of it as a force with two parts. One part that's parallel to the ramp and another part that's perpendicular to the ramp. Question is, what are those two pieces? Well, if I know this angle, and most of the time in physics class they give us that angle, I can find this angle and I can also find that angle. So this angle, because that would make a right triangle, that's going to be 90 minus 35. That's going to be 55. Or this angle over here, that has to be 35 as well. So you can split this into components. You can label them relative to the 55-degree angle or the 35-degree angle. Either one is fine. And it actually, you don't even have to be consistent. But basically, part of this weight is pulling us down the ramp, and it goes this way. That's the component parallel to the ramp, so it's the projection of this weight onto the ramp. And now there's another part of the weight that's perpendicular to the ramp. That's keeping the box on the ramp. Now you might say, Miss Townsend, the box is not going through the ramp. Well, there's other force, a normal force, that's balancing that. But that's beyond the scope of this class. Talk to your physics teachers about the normal force. All we want to do is we want to take this weight and we want to break it into two parts. This part that's parallel to the ramp and another part that's perpendicular to the ramp. And notice if I add this force and this force together, I get mg back. So let's talk about, I'm going to call it the weight, use W for weight, the part that's parallel to the ramp. Well, since that's adjacent to the 55, I'm going to get the hypotenuse of that triangle, which is mg, mass times gravity, where we're just using the scalar 9.81 meters per second squared for gravity. And then since this is next to the 55, the side is, but it's not the hypotenuse, that's the adjacent side, adjacent to 55. So we're going to have a cosine of 55 there. And then the part that is perpendicular to the ramp, or since we're dealing with a ramp, we might say that this vector, this vector is normal to the ramp. That's the magnitude of the hypotenuse, and since it's opposite the 55 in the triangle, we're going to get a sine of 55. So you've done this before. That's a projection, and that's the vector component that's orthogonal to that projection. You've got one that's parallel to the ramp and one that's orthogonal to the ramp. Or one that's parallel to the ramp, since we're talking about a ramp, one that's normal to the ramp. So box on a ramp, baby on a slide. truck on a hill, all of them are the same thing, and you've done this. Now, in our class, in math class, most of the time we don't know this angle. All we have are u and v in component form, and I can draw a picture like this. If I have the components of u and the components of v, the question becomes, how do I find the equation of the vector projection of u onto v? And how do I find a formula or an equation for the vector component of u that's orthogonal to v? That's actually not too bad, just using some simple trig. So let's focus on first just the length of the projection of u onto v. I'm going to draw my picture again. I'm going to try to draw it a little bit bigger. I'm just going to give myself a little bit more space. Make u longer. That's u. This is my vector v. And to find the component of u that's orthogonal to v, I'm just going to use a straight edge from another piece of paper, create a right triangle. That's w. And then this down here, this is the part of u that's parallel to v. We call it the projection of u onto v, the vector component parallel to v, and we're right there. And notice that this is u and v with their tails meeting at the same place. If their tails meet at the same place, or we start at the same place, the angle between u and v is theta. So using this picture, it's pretty easy to see what the length of this projection would have to be. So the length of the projection, or the magnitude of the projection of u onto v, just using trig, well, that's on the adjacent side of my triangle. I've got the hypotenuse here. Cosine is adjacent over hypotenuse. So adjacent is hypotenuse times cosine of theta. Now, if theta happens to be acute, we're good, because cosine of theta is positive in that case. But if theta happens to be obtuse, so that u is actually over here, this might be a negative number. And the length of this projection vector, it can't be negative. The length is either 0 or it's positive. So we need to put some absolute value bars around this. And notice this is just exactly what we did over here. When I wanted the projection of this force mg onto the ramp, I just took the part of the force that was parallel to the ramp, that was next to the 55. I had mg, so that's the magnitude, times the cosine of 55, because it was adjacent to the 55, that side was. That's what I have here. I've got the magnitude of my force times the cosine of this angle, because I'm on the adjacent side. Now, I'm not going to use this because I don't typically know theta. I typically know v, or u and v, in component form, and I can use this to derive the formula for the length of the projection of u onto v. Does this remind you of something? I hope it reminds you of this. It's our geometric definition of dot product. Look, there's that side. It's the length of u times cosine of theta. This is the same thing. It's the length of u times cosine of theta. It's an absolute value, but it's very close. If I wanted this to be a dot product, all I would have to do is multiply by the length of v. And I can do that. It doesn't change the value, as long as I also divide by the length of v. Then these are exactly the same thing. So now in my numerator, I've got the absolute value of the length of u times the length of v times the cosine of the angle between them. That is the absolute value of the dot product. Remember, the dot product is a scalar. We're just taking the absolute value of that number, and we're dividing by the length of v. So this is called the scalar projection of u onto v. And that is just the component of u that's parallel to v, and it's just the length of that side. That's what the scalar projection is. Or the magnitude of that. That's what that is. Now, if I want the vector projection of u onto v, I'm talking about a vector now. Well, I know that this vector has the same direction as this vector v, and I know the length is supposed to be this. And then there are only two options for the projection. If the projection and the vector v are pointed in the same direction, I just take the length and I multiply by the unit vector in that direction. If the projection and v are pointed in opposite directions, maybe because our u is over here, and I'll have to show you a picture of that where theta is obtuse, and so our projection is on this side. Then the projection and v are going to be in opposite directions rather than in the same direction. So here's what we're going to do. We're going to take this, but to account for the fact that sometimes the projection goes in the same direction as v, and sometimes it goes in the opposite direction as v, I'm going to drop the absolute value. That's the signed length. And then I'm going to multiply that by the unit vector in the direction of v. To find the unit vector in the direction of v, we just take v and we divide by its magnitude. Now, before I simplify this any further, I just want to show you if u dot v is positive, so the angle between u and v is acute. This is just a positive number divided by a positive number. So I've got a scalar here, then I've got a vector divided by a scalar. So I can simplify this. This is u dotted with v. Length of v times the length of v is the length of v squared. That's a number, and we're multiplying that by the vector v. So I've got a scalar times v, and that's the projection of u onto v. I think that makes sense. We're talking about the part of u that's parallel to v. It either goes this way or it goes that way. Now, if theta is acute, it goes that way, and this is a positive number. Now, if theta is obtuse, remember the dot product is negative when theta is obtuse, so I've got a negative number in that case times v, and it would just go in the opposite direction. And that's exactly what we want. So this is the vector projection. Of u onto v. Okay, I just want to show you, this is with theta acute. Let me show you one more picture. Let's say theta is obtuse. Maybe this is our vector v, and instead we've got a vector u that looks like this. So u is pointing roughly in the opposite direction from v. So that's my theta. Now when I want to find the projection of u onto v, it actually looks like it doesn't overlap with v at all. I've got the sun here, and I want to know what is the part of u that's parallel to v. It's just that part. So the projection of u onto v in this case, that points in the opposite direction from v. And then the component of u that's perpendicular to v, or orthogonal to v, that w, that still points this way. So if theta is obtuse, your projection and your vector v go in opposite directions. And that's exactly what we would see here. If theta is obtuse, the dot product is negative, so I've got a negative number times v, so I'm going to go in an opposite direction from v. If theta is acute, the projection of u onto v and v are going in the same direction, so I end up with a constant times v here. Now the question becomes, okay, you've got a scalar projection. We know what that is. If I know the angle, I can just do that. If I don't know the angle, I can do that. And then I say, okay, well, it's a scalar projection. What if I want the vector projection? I just multiply by the unit vector in that direction. Had to drop the absolute value because sometimes they go the same way and sometimes they go the opposite way. And so we have this. I'm going to call this the signed length. Okay. All right, now the question becomes, how do we find W? Well, W is actually not so bad because of this fact right here. W is just the vector that I add to the projection to get U back. It's the part of U that's perpendicular to V. So there's part of U that's parallel to V, that's the projection, and the other part that's perpendicular to V. If theta is acute, it looks like this. If theta is obtuse, there's part that's parallel to V, and there's part that's perpendicular to V. Still, same thing. But if I add this vector and this vector tip to tail, I should get U back by design. So finding W really isn't that difficult. W plus the projection of U onto V has to be U. So if I want to find W, I just solve for this guy by subtracting the projection from both sides. So we're going to have W equals U minus the projection of U onto V. And this is the vector component of U perpendicular to V, or since we're talking about vectors, we're going to say orthogonal to V. We're still going to use that little perpendicular notation from geometry class from high school. All right. So now we've got our formulas. I'm having a quiz over this material. Of course, I would love for you to know where all of these formulas come from. But if not, just make sure you've got your formulas on your sheet. The length of the projection of U onto V is the magnitude of the dot product divided by the length of V. The vector projection of U onto V is just the dot product divided by the length of V squared times the vector V, and that's just a number times V, and W satisfies this. So if I get W by itself, I have W equals U minus the projection. Okay, so these are what I'm going to use when I go through the next few examples. Actually, I think I'm going to stop here and make a separate video for examples. So stay tuned for that.